Balancing ionic equations. Ionic equations are those chemical equations which represent chemical reactions involving ionic substances in their aqueous solutions. Let us take an example to understand it better. What really happens when you put AgNO3 and NaCl both in water? AgNO3 in aqueous state reacts with NaCl in aqueous state to give AgCl in solid state plus NaNO3 in aqueous state. Key point is sodium chloride actually means the sodium ions and the chloride ions are present in aqueous state. These exist as dissociated ions or ions in solution. Magnesium nitrate in aqueous solution really means that the magnesium ions and the nitrate ions are in dissociated form or ionic form. MgNO3 whole twice in aqueous state really means magnesium positive 2 ions in aqueous state plus NO3 negative 1 ions in aqueous state. That is dissociated ions or ions in solution. Let us first try to understand what is dissolving. When an ionic compound, for example, a salt dissolves in water, the compound dissociates. That is, it breaks apart into cations and anions. Example, CaNO3 whole twice in solid state gives Ca 2 positive ions in aqueous state plus 2 NO3 negative ions in aqueous state. When a covalent compound, for example sugar, dissolves in water, the molecules simply disperse. They do not dissociate. Molecules of the covalent compounds simply disperse due to attraction with polar water molecules. Key point: AgCl in solid state really means solid silver chloride. Let us take an example to understand it better. What really happens when you put silver nitrate and sodium chloride both in water? Silver nitrate in aqueous state reacts with sodium chloride in aqueous state to give silver chloride in solid state plus sodium nitrate in aqueous state. Here, silver nitrate dissociates into silver ions and nitrate ions. Sodium chloride dissociates into sodium ions and chloride ions. Silver ions combine with chloride ions to form silver chloride precipitate. Sodium ions and nitrate ions remain in solution. Silver chloride in solid state settles as a precipitate at the bottom of the container. Only sodium ions and nitrate ions remain in solution in ionic form. We can say that sodium nitrate is present in aqueous form. So, we can say that AgNO3 in aqueous state reacts with NaCl in aqueous state to give AgCl in solid state plus NaNO3 in aqueous state. The complete ionic equation can be written as Ag positive ions in aqueous state plus NO3 negative ions in aqueous state plus sodium ions in aqueous state plus chlorine ions in aqueous state give AgCl in solid state plus nitrate ions and sodium ions. This means that reaction has taken place between silver and chloride ions to form silver chloride. No reaction takes place between sodium ions and nitrate ions. This means these ions do not participate in the reaction. They are called spectator ions. The net ionic equation is constructed from the complete ionic equation. Crossing over the spectator ions, we get silver ions in aqueous state plus chloride ions in aqueous state gives solid silver chloride. Let us revise. Complete molecular equation describes double replacement reaction. Complete ionic equation more accurately shows the reacting species as ions and the products either as ions or a precipitate. Net ionic equation focuses only on the ions reacting. Spectator ions are those ions that are present in solution but do not participate in the reaction. We can say that a chemical equation written in terms of ionic symbols is called an ionic equation. For example, the equation shown on screen is an ionic equation. Zn in solid state reacts with two H-positive ions in aqueous state to give Zn 2 positive ions in aqueous state plus H2 in gaseous state. Similarly, copper ions in aqueous state react with zinc ions in solid state to form zinc ions in aqueous state, and copper is formed in solid state. This is also an ionic equation. It is not necessary that all the reactants and products of a chemical reaction be expressed as ions for it to qualify as an ionic equation. So, Cd 2 positive ions in aqueous state react with H2S in gaseous state to give CdS plus 2 H positive ions in aqueous state. Equation on screen is also an ionic equation. Hydrogen sulfide and CdS are written in unionized form. A few examples of ionic equations are shown on screen. Hydrogen chloride in an aqueous form reacts with sodium hydroxide in an aqueous form to form sodium chloride in an aqueous form and water in liquid form. Hydrogen ions, chloride ions, and hydroxide ions in aqueous state react to form sodium ions, chloride ions in aqueous state, and water in liquid state. Cancelling out any positive and Cl negative ions on both sides of the equation, the new ionic equation becomes H positive ions in aqueous state plus OH in aqueous state give H2O in liquid state. From this equation, we find that a neutralization reaction between an acid and a base has taken place. Let us discuss another neutralization reaction. The reaction between potassium hydroxide and hydrochloric acid in an aqueous solution can be written as KOH in aqueous state reacts with HCl in aqueous state to give KCl in aqueous state plus H2O in liquid state. K positive ions in aqueous state plus OH negative ions in aqueous state plus Cl negative ions in aqueous state give K positive ions in aqueous state plus Cl negative ions in aqueous state plus H2O in liquid state. On cancelling out the common factors of K positive in aqueous state and Cl negative in aqueous state on both sides of the equation, the new ionic equation becomes H positive ions in aqueous state plus OH in aqueous state gives H2O in liquid state. We can conclude that neutralization is mainly the formation of water from H positive ions in aqueous state and OH negative ions in aqueous state. The reaction of zinc metal with dilute sulfuric acid can be represented in the form of an ionic equation, which can be represented as shown on screen. Zn in solid state reacts with 2H positive in aqueous state to give Zn 2 positive ions in aqueous state and H2 gas. Instead of Zn in solid state reacts with dilute H2SO4 to give ZnSO4 in aqueous state and H2 in gaseous state. We will take another example. When H2S gas is passed through a solution of cuprous ions, Cu 2 positive ions, a black precipitate of copper sulfide and hydrogen ions are formed. The representation of a reaction of this kind has an added advantage that the above ionic equation is applicable for solution of cuprous ions obtained from any ionic source of copper like copper sulfate, that is CuSO4, copper nitrate, CuNO3 whole twice, copper chloride, CuCl2, and so on. When zinc metal is added to solution of cuprous ions, Cu 2 positive ion, it dissolves to form Zn 2 positive ion and the copper metal gets precipitated. The source of cuprous ions, that is Cu 2 positive ions, can be any water-soluble salt of copper, like copper sulfate, that is CuSO4, copper nitrate, CuNO3 whole twice, copper chloride, CuCl2, and so on. We will now discuss about balancing ionic equations. Ionic equations, like ordinary chemical equations, should be balanced in terms of the number of atoms of all kinds. Additionally, an ionic equation must also be balanced with respect to the number of charges on both sides. The skeletal ionic equation involving aluminium metal and an acid that liberates hydrogen gas can be written as Al in solid state reacts with H positive ions in aqueous state to give Al 3 positive ions in aqueous state plus H2 gas. Such equations must be balanced first for the number of atoms or ions only. That is, element aluminium, the number of atoms on left-hand side is 1 and the number of atoms on right-hand side is also 1. Element hydrogen, the number of atoms on left-hand side is 1 and the number of atoms on the right-hand side is 2. Balance the number of hydrogen atoms by putting 2 before hydrogen ions in aqueous state. The new equation becomes Al in solid state reacts with 2 H positive ions in aqueous state to give Al3 positive ions in aqueous state and H2 gas. This equation is balanced with respect to aluminium and hydrogen atoms, but this is an unbalanced equation with respect to charges. In order to balance it completely, put 6 before H2 positive ions in aqueous state instead of 2 and 2 before Al3 positive ions in aqueous state to make 6 positive charges on both sides. Al in solid state reacts with 6 H positive ions in aqueous state to give 2 Al3 positive ions in aqueous state and H2 in gaseous state. Again, balance the aluminium atoms by putting 2 before Al in solid state and 3 before H2. 2Al in solid state reacts with 6 H positive ions in aqueous state to give 2 Al3 positive ions in aqueous state and 3 H2 in gaseous state. This equation is completely balanced both with respect to its number of atoms and the number of charges, and thus can be called a completely balanced ionic equation. Children, let us balance the following ionic equation. Cu2 positive ions in aqueous state react with Fe in solid state to give Fe 3 positive ions in aqueous state and Cu in solid state. Solution is: on inspection, it is clear that the number of atoms on both sides of the equation is same. 1 atom or ion of Fe and 1 atom or ion of Cu. So, it only needs to be balanced with respect to charges. To make charges equal on both sides, put 3 before Cu2 positive ions in aqueous state and 2 before Fe3 positive ions. But during the process, the number of atoms becomes unequal. To make them equal, put 2 before Fe in solid state and 3 before Cu in solid state. The equation thus becomes 3Cu, 2 positive ions in aqueous state react with 2Fe in solid state to give 2Fe 3 positive ions in aqueous state and 3Cu in solid state. This equation is completely balanced.